Alright, so now we're going to look at some more complicated situations where we can't directly get to an inverse function from what we're given. But we'll need to use some identities and or factoring to solve the equations. So consider this example. Here we're asked to solve 2 sine square x plus 1 is equal to 3 sine x, and we're asked to solve this over the interval 0 to 2 pi. Well, just using a little bit of algebra, I can subtract 3 sine x from both sides, and I can rewrite this as 2 sine square x minus 3 sine x plus 1 equals 0. So now, if we look at this, I have the sine function and the square of the sine function. So this is like solving, right? So this is like 2u squared minus 3u plus 1 equals 0, where I've made the substitution that sine x is u. Now, you've learned how to solve equations like this in the past. You've learned how to use factoring to solve this. So if you remember how to factor, this factors as 2u minus 1 by u minus 1 equals 0. So then u equals 1/2, or u equals 1. Now if you don't remember how to factor, I'm going to post some other links in the course for some factoring reminders. Now, if you're just not good at factoring, remember you can also use the quadratic formula. So since this is a quadratic equation in standard form, u is equal to the opposite of -3 plus or minus the square root of -3 squared minus 4 by 2 by 1 over 2 times 2. And so then u is equal to 3 plus or minus the square root of 9 minus 8 over 4. 3 plus or minus the square root of 1 is 1 over 4. Alright, now 3 minus 1 is 2. 2 over 4 is 1/2. Or 3 plus 1 is 4. U equals 4 over 4, which is 1. The same two values, just a different way of getting it. And of course, if you're good at factoring, I think the factoring's easier. If you're not good at factoring, the quadratic formula works, takes a few more steps, more chances for arithmetic errors. Okay, now, we're not done. Because we weren't asked to solve for u, we were asked to solve for x. We made a substitution. We said that the u was sine x. So now taking our two values, right, taking these values, u equals 1/2 and u equals 1, that really means then that sine x is 1/2 or sine x is 1. Alright, so then over 0 to 2 pi, if sine x is 1/2, well, we've seen this situation before. If sine x is 1/2, then x is pi over 6, or x is 5 pi over 6, just using reference angles, a unit circle. Sine x is 1, where the b coordinate is 1, that would mean x is pi over 2. So over 0 to 2 pi, there's actually 3 solutions to this equation, and I'm just going to put them in numerical order. Pi over 6, pi over 2, 5 pi over 6. Alright, so here, to solve this equation, we had to get this equation into a quadratic form, and then use either factoring or the quadratic formula to come up with roots to the quadratic part, and then we had to use some trigonometric understanding. Let's see another example. Alright, so here we're asked to solve sine 2x is equal to 2 sine square x, again over 0 to 2 pi. Now, the issue with this situation is, see how on the right-hand side I have the square of sine x. The argument is x. But here, on the left-hand side, the argument is 2x. Since those arguments don't match up, I have difficulty. I can't use just algebra to solve this. So, instead, I'm going to use an identity first. Recall that sine 2x is the same as 2 sine x cosine x. And that's still equal to 2 sine square x. Now, I have everything in terms of the argument x. Right? There's no 2x involved anymore. Now everything's in terms of x. Now I can use factoring. It's very tempting to divide out that sine x. But if you divide out the sine x, you'll lose solutions to the equation. You don't divide by a variable. When solving an equation, you don't divide by a variable factor. You use factoring. So what I'll do instead is I will write this, let me write this as 2 sine x cosine x minus 2 sine square x is 0. And I see that I have a common factor of 2 sine x. Let me factor that out. 2 sine x times cosine x minus sine x is 0. So then using the zero factor or zero product property, this means that 2 sine x is 0, or cosine x minus sine x is 0. Alright, so if 2 sine x is 0, that means that sine x is 0, and so then over 0 to 2 pi, x would equal 0, pi, or 2 pi. That's where the sine is 0. Cosine x minus sine x equals 0. Well, that's the same as saying where is the cosine x equal to the sine x. And so if we think about the unit circle, think about what we understand so far. The cosine and the sine are equivalent. Those are at a couple of pi over 4 angles. So that would be x equals pi over 4. Right? In the first quadrant, the a coordinate is equal to the b coordinate at pi over 4. And at the third quadrant, at 5 pi over 4. So there's actually 5 solutions to this equation. And just putting them in numerical order, the solutions are 0, pi over 4, pi, 5 pi over 4, and 2 pi. So here we had to use an identity first to get the equation into a form where we could then use factoring. Alright, so when do we use identities? Well, generally speaking, if the arguments are different. So in that last example, we saw that the arguments were different. We had a sine function, right? We had sine x, and we had a sine 2x. The arguments were different. We had to use an identity to get the arguments to be the same. Another situation would be if the functions are different. If we had something in terms of sines and something in terms of cosines, that might be difficult. We might have to use an identity to get that to a situation where we could work with it. So let's see another example. Alright, so I'd actually like for you to pause and try this one out on your own. And what I would say is, notice that I have that second situation from the previous slide. That I have something in terms of sines and something in terms of cosines. Can you get everything in terms of one of those functions? Now would be a good time to pause and try it on your own. Alright, so again, what I see is I have the cosine of x and I have the sine of x. And I don't know if I can work, I've got sine square. I can't get this to be a simple situation directly. But I do remember that I can use the Pythagorean identity to write sine square x as 1 minus cosine square x is still equal to 3 minus 4 cosine x. And so now this equation is quadratic in terms of the cosine function. So, using a little bit of arithmetic, let's bring that cosine square x over, let's bring that 1 over. I have 0 is equal to cosine square x minus 4 cosine x plus 2. So now this is quadratic in cosine x. And so I can apply factoring. Well, factoring is not going to work here. There's no way I can get two numbers that multiply to 2 and add a negative 4. So factoring won't work. I have to use the quadratic formula. So cosine x is equal to the opposite of negative 4, plus or minus the square root of negative 4 squared, minus 4 by 1 by 2, over 2 times 1. Cosine x is equal to 4 plus or minus the square root of 16 minus 8, it's 8, over 2. Cosine x is equal to 4 plus or minus the square root of 8 is the same as 2 times the square root of 2, over 2. So cosine x is equal to 2 plus or minus the square root of 2. So let's break that up into two situations. Cosine x is equal to 2 minus the square root of 2. Cosine x is equal to 2 plus the square root of 2. Now I know that the square root of 2 is about 1.4. So 2 minus the square root of 2 is approximately 0.6. 2 plus the square root of 2 is 3.4 approximately. The cosine cannot be 3.4 because remember the range of the cosine function is negative 1 to 1. 3.4 is outside of that, so I can throw this away. Cosine x can be approximately 0.6. There are two places on the unit circle. Let's think of our unit circle for a moment. The cosine is positive and approximately 0.6 there. So I'd have one solution in quadrant 1, a second solution in quadrant 4. The solution in quadrant 1 is given by the inverse function. So then x is equal to the cosine inverse of 2 minus the square root of 2. That's my first angle from the inverse function. The second solution, well, I'd go all the way out to 2 pi and subtract the reference angle. So x2, the second solution, would be 2 pi minus cosine inverse of 2 minus the square root of 2. And there are the two solutions of this equation over 0 to 2 pi. Alright, let's consider one more example. So here we have the equation 3 times cosine x minus 3 times sine x equals 0 over 0 to 2 pi. So again, now would be a great time to pause, try this one out on your own. Alright, did you pause? Did you try it on your own? So there's a few ways we could solve this. Here's how I would look at it. Cosine x times cosine x is cosine square x. And so then this is 3 times cosine square x minus 3 times sine square x equals 0. So now, if we did a little bit of factoring, I could think of this as 3 times cosine square x minus sine square x is 0. And I look at that and I say that cosine square x minus sine square x, I remember something about that. That is the cosine, that's the identity for cosine 2x. So this is the same as 3 times cosine 2x is 0. So I can divide by 3. Cosine 2x is 0. And then now, where is 2x? So where is the cosine equal to 0? The cosine is 0 at several places, right? whereas the cosine 0, 2x, is equal to, let's see, the cosine is 0 at pi over 2 and 3 pi, I wrote pi over 3, pi over 2 and 3 pi over 2 plus 2 pi times k, and then divide by 2. So then x is equal to pi over 4, 3 pi over 4, plus pi times k. And so then if we're only looking over 0 to 2 pi, we could take the pi over 4 and add pi, and the 3 pi over 4 and add pi. And so over 0 to 2 pi, we'd have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And those are the solutions over 0 to 2 pi. Another approach one could take would be, from this point, we could rewrite this as 3 cosine square x equals 3 sine square x. And let me divide through by the 3 cosine square x. We don't usually like to divide through by variable factors, but it works in this situation. So then 1 is equal to, the 3's divide out, sine square x over cosine square x is tangent square x. So tangent square x equals 1, and then applying the square root property, tangent x is plus or minus root 1. Tangent x is positive or negative 1, and then over 0 to 2 pi, that gives us the same 4 solutions. Either way works. But in either of those situations, you had to use an identity of some form or another. Alright, that completes the third part of this lesson.